So SPC4 is on the topic of internal resistance. What we're going to do is we're going to introduce a couple of new terms, which is EMF, which stands for electromotive force, and internal resistance. And we're going to see what they are and what sort of effect they have upon circuits. So the problem with the real world is that we don't get these lovely ideal power supplies that we've been discussing so far. So everything that's made out of anything is going to have some resistance associated with it until we get into the region of superconductors. Whoops. But that's a way off yet. So everything's made out of resistance, so of course the power supplies, everything has a resistance, so the power supplies themselves must have some sort of resistance associated with them. So yes, they're putting this voltage across the circuit and they're pumping this current around, pumping the energy in, but when that current passes through the power supply, it must also incur some sort of resistance, and so that's going to affect the performance of the power supply and what sort of effect it has on the circuit. And we'll see later that what it means is that the higher the current in the circuit, the worse the impact is going to be on the performance of our circuit. So we've got ourselves a nice little diagram here to sketch what's going on. So previously we would have just had the cell over here. We can see we've got a circuit, an ammeter, a voltmeter, a load, and that's connected up to our power supply, so our battery or our cell or whatever. But we've done it slightly differently. Rather than just having the cell, we've kind of imagined inside our cell we've got our ideal cell, but then we've also got a resistor in there, so our internal resistance, and that represents the resistance that the real cell has. So we're modelling our real cell as an ideal cell in series with a little resistor or a large resistor, depending on what the cell is. And so this EMF, the electromotive force, that's the voltage which is output by the ideal cell to the entire circuit. But that voltage has to be shared not only with the external load, so any resistors outside the cell, but the internal load is going to take some of that resistance as well. So if we have some current passing through the supply, and we have an internal resistance which we typically denote with a lowercase r in the cell, and we also have the terminal potential difference. So the difference between the EMF and the terminal PD is the EMF is what's put out by the ideal cell inside our real cell, and then the terminal PD is what actually reaches the circuit. So some of the EMF we said is going to be lost inside this internal resistance, and so only some of the EMF is actually going to make it to the external circuit to drop across whatever the resistors we've got on the load. So that's our difference between the EMF and the terminal PD. And so this means that the difference between the EMF and the terminal PD is known as lost volts. So that's a key term here. So we say that because our real power supply has some internal resistance associated with it, there are some loss volts which are dropped within the power supply before our EMF even gets to the rest of the circuit. So only some of the EMF is going to get to the external circuit in order to power up whatever external load, or be it resistor, bulb, etc., that we're trying to supply. So this is what's lost, driving the current through the internal resistance. And so how do we measure this? Well, V equals IR according to Ohm's law, and so if we have some circuit passing through our current passing through the circuit, then the voltage drop across this internal resistance is going to be our voltage drop is equal to the current times the internal resistance. And so what's going to be left as the terminal PD, so uppercase V, our terminal PD, is going to be whatever the original EMF is minus these lost volts, so minus what's been lost here. So we've got our total EMF trying to power up the entire circuit, but then we lose a little bit of it due to the internal resistance, and so what we're left with is the terminal potential difference, which is what the rest of the circuit is seeing. And we can work out what this current is because we can model this now as an ideal cell with two resistors in series. So we could use the EMF and these two resistors, sum them up as resistors in series, and that'll tell us the total resistance and the voltage. That'll tell us the current passing through the circuit, which we can then stick into this equation and say, okay, that's our current, so that means we've lost how many volts from the EMF to leave us with what terminal PD. And so we can see that the higher the current, the larger these lost volts are going to be, and so the smaller the terminal PD is. So if we've got an extremely high load on the outside, we're going to have a very low current, and so the voltage which the external load is going to see is going to be almost the entire EMF. The loss volts are going to be small. If we've got a very small load on the outside, so a very low resistance load, then that's going to result in a very high current, which will mean that a large portion of the EMF is being dropped across the lost volts, and only a small terminal PD is actually seen outside. And so this is the problem with when we short circuit our power supplies. We end up having a huge current passing through the internal resistance, which means there's a huge amount of power being dissipated inside the cell itself, which causes things to heat up and break and set on fire and the like, and it's generally not very good. We'll cover power formally next lesson though. During the lesson, you're going to have a little do a little exercise where you'll see what exactly how much of an effect this has. You'll yes. So you'll do a little experiment, and you'll be able to plot graphs based off of this. So if we flip back here, let's write out our loss volts equation. So y equals mx plus c, and v equals epsilon minus IR. And so if we were to plot a voltage current graph, rather than the ideal graph that we were getting before, of course that's a lowercase r, isn't it? Excuse me. And so actually this is all backwards again, isn't it? So what we've really got is lowercase r, uppercase I, except there's a minus there, and we're going to have plus EMF. So for a real cell, if we have some resistance, if we have the internal resistance and we vary the voltage and the current, so we can have an external load and vary one or the other, vary the load so that we affect the total current passing through the circuit, we'll be able to measure the terminal PD across the cell. We'll be able to measure the current passing through the circuit, and if we plot those, what we're expecting is that on a voltage current graph, so let's get that out, V against I, we're expecting a negative gradient equal to the internal resistance of the cell. So this time the gradient is going to be the internal resistance of the cell. And we're going to have a y-intercept, which is going to actually be the EMF. So we're expecting a straight line graph with a negative gradient. So this here is going to be the EMF, and the gradient along here is going to be the internal resistance of our cell. So this lesson we've had a brief introduction into when we move away from our ideal physics classroom, we get into the real world and we get real problems with real power supplies having a real resistance. And depending on the current that's flowing through a circuit, this might have a fairly negligible effect, or it might have a considerable effect, and we'll have to take that into account when we're planning our circuits. So there we go.